Autumn Park 2020 cohort. My name is Mr. Tipler. I am one of the curriculum leaders for maths at Autumn Park, and I hope you're all as excited as I am about joining us in September. I can't wait to meet all of you and see all your faces in September. Like I said, I'm one of the curriculum leaders for maths. So today we're going to be doing a bit of a math lesson, and we're going to be exploring ratio, proportion, and sequences, and looking at them in real world and where they apply in real world. In particular, we're going to look at something called the golden ratio. Some of you may have heard of it before. Okay. Some of you may have not, but we're going to look at where this occurs in real life. So in nature, in art, in architecture. Okay, just showing how mathematics is the language of the universe and how it occurs everywhere. So we're going to be taking a look at proportion in the real world. Okay, and we're going to explore the golden ratio and how golden you are. So as a little starter, what I'd like you to do is practice your sequences. Okay, I want you to find the rule and the next 3 terms for each of these sequences. Okay, so what I'd like you to do is pause the video, grab a pen and paper, okay, and see if you can just find the next 3 terms in each of these sequences and the rule that from term to term, what's happening each time. So pause the video and give this a go. Okay, hopefully you've managed to do all of them. If you didn't, that's not a problem. Let's see if you got them all right. So the first one, we've got 1, 4, 7, 10. Okay, we can see that that's going up by 3 each time. So the next one's going to be 13, then 16, then 19. Then the next one, we've got 11, 24, 37. That time it's going up by 13 each time. Okay, you might see a similarity in the units digit from A, but it's going up by 13 each time. So the next one's going to be 50, 63, 76. The next one, 40, 34, 28. This time it's going down, so it's a subtraction. We're subtracting 6 each time. So it's going to be 22, 16, 10. And then for D, we've got 11, 8.5, 6. A tricky one, this one. It's subtracting again. It's going down each time. It's going down by 2.5. So 6 take away 2.5 is 3.5. And then take away 2.5 again, we get 1. And we take away 2.5 again, we get into negatives. It's minus 1.5. Okay, well done if you got that one. That's a tricky one. Next one is minus 6, minus 4, minus 2. Okay, this time starting in the negative numbers are going up by 2 each time. So minus 6, minus 4, minus 2. Then add 2, it goes 0, 2, 4. Okay, so well done if you got that and you got the negative number bits right. Okay, the next 5 are a little bit different because all the ones so far are either adding or subtracting. This time they're not adding or subtracting each time. So we go from 3 to 6 to 12 to 24. That time they're doubling each time. So we're multiplying by 2. So the rule is times by 2. So the next one's going to be 48. And then 48 times 2 is 96. And 96 times 2 is 192. The next one starts with a decimal, 0.2. Then 2, 20, 200. The rule for this one is that we're multiplying by 10. So adding a 0 each time, but we're multiplying by 10. So we have 2,000, then 20,000. Going to run out of space. And then the last one, 200,000. Okay, the little H, we've got 160, 80, 40. What's happening there is that they are halving each time. So we're dividing by 2. So 2 previous ones we were timesing by a number. In this one, we are dividing by 2. So the next one would be 20. Half of 40 is 20. Half of 20 is 10. And then half of 10 is 5. 1, 3, 9, 27. In this one, we are multiplying by 3. So tripling each time. So the next one is 81, 243, and then 729. Okay, well done if you got those. And then for J, goes 2, then negative 4, then positive 8, then negative 16. So it's a tricky one. Hopefully you spotted that the numbers are doubling, but it's going from positive to negative. So 2 patterns going on each there. But what's actually happening is we're multiplying by minus 2. So 2 times negative 2 is negative 4. But then when you times a negative number by another negative number, it becomes positive. So minus 4 times 8 is also times by negative 2. So the next one's going to be positive 32. Then negative 64, and then positive 128. Okay, if you got 10 out of 10, okay, give yourself a pat on the back. That's great work. Well done. So we're going to explore another sequence. Okay, a very special type of sequence, my favorite sequence. Okay, so what I want you to do is see if you can, the sequence is going to come up on the screen. I'm going to want you to pause the video, give yourself 3 minutes, okay, to see how far you can continue the sequence, find as many of the terms as you can, okay, so spot the pattern. So here's the sequence, okay, pause the video. How many terms in this sequence can you find? It starts off 1, 1, 2, 3, 5, 8. Okay, how many terms in this sequence can you find? Okay, if you're not sure and you're looking for a hint, I'll give you a hint now. Okay, think about how two terms, these two terms are related to this term, and how these two terms are related to this term. Okay, so now pause the video, give yourself 3 minutes, continue the sequence as far as you can. Okay, so hopefully you've given yourself that time. So what the rule is that you add the two previous terms to get the next term. So 1 and 1 gives me 2. 1 and 2 gives me 3. 2 add 3 is 5. 3 add 5 is 8. 5 add 8 would give me the next term, 13. 8 add 13 is 21, so the numbers start getting a bit bigger quite quickly. 13 add 21 is 34. 21 add 34 is 55. Okay, and hopefully you found a lot more than that. But we're going to stop at 55. Okay, and the sequence goes on forever. Have you seen the sequence before? Do you know what it's called? Okay, if you haven't, that's absolutely fine. It's called the Fibonacci sequence. Okay, so Fibonacci, pronounced Fibonacci. Okay, and it's where the sum of the two previous terms make the next term. It's named after a Italian mathematician who was alive in the 12th and 13th century. Okay, so 800 years ago, called Leonardo Fibonacci, and that he was the first sort of person that discovered the sequence and looked into it. Okay, so actually, what we're looking at today was first really discovered by the ancient Greeks, so 1,000 years before that. But Fibonacci was the first person that linked this so-called golden ratio with the Fibonacci sequence. Okay, and one thing that comes out of the Fibonacci sequence is if we look at a geometrical, so something to do with shape, interpretation of it. So if we start off with a 1 by 1 box, so apologies for my terrible drawings, okay, but we start off with a 1 by 1 box because that's the first time in the sequence, and then we draw another 1 by 1 box, okay, and then we have a 2 by 2 box, so 1, 1, 2, and then a 3 by 3 box, and then a 5 by 5 box, and then we get an 8 by 8 box. We just go round and round the square like that. Okay, drawing squares each time. Okay, and it's going to look like this picture here. And then if we draw a spiral around it, oh, that's going the wrong way. It will look like that diagram there. Okay, it will look like this diagram here. So this is known as the golden spiral. Okay, and it's a geometrical interpretation of Fibonacci's sequence. And this spiral comes up in lots of different areas in the world. So in nature, it's seen in architecture, and it's seen in art, okay, and even in us as well. And we're going to talk about and explore this spiral and also something else called the golden ratio. So here's this spiral again. We can see that actually the petals or the leaves on this plant, okay, the way they go around this number of petals in each row of the sequence, each row on the plant is the sum of the rows before. So that's the Fibonacci sequence. Okay, as well, the petals on a sunflower or the seeds on the sunflower, they have this golden spiral in there as well. Even the shell on this snail, these have the golden ratio. golden spiral within that shell as well, and even in a hurricane. So it's something we can see there that the spiral is overlapped over the hurricane, but we can see that in nature this golden spiral occurs everywhere. So we're going to delve a little bit deeper into the Fibonacci sequence now, and what we're going to do is calculate the ratio between each terms. Okay, and what I mean by that is we're going to find what do we have to times by the previous term to get to the next term. Okay, so the way we do that is we take one term and divide it by its previous term. So we're going to do 1 divided by 1, that's 1. Then we're going to 2 divided by 1, that's 2, nothing that interesting so far. 3 divided by 2, 1.5, so it's got bigger and then smaller again. 5 divided by 3 is 1.6, so it's got bigger again. No, it's not, it's 1.6 recurring, so it's 1.66666. Okay, so 5 divided by 3, 1.6. And then do 8 divided by 5, see what you find, okay? So hopefully you went for your Fibonacci sequence, you went further than 144, okay? So do it for as far as you got. So how far did you get on your Fibonacci sequence? Do the term divided by its previous term to find the ratio between those two terms. Okay, so pause the video and give that a go. Okay, so hopefully you've gone all the way to the end of your Fibonacci sequence dividing the term by its previous one. So for this case, let's do 144 divided by 89. Okay, I'm going to need my calculator for that. So 144 divided by 89 is, you see that, 1.6179. So I'm going to round that to 3 decimal places, 1.618. So 1.618. Okay, so actually hopefully what you found is that 8 divided by 5 was 1.6. Okay, 13 divided by 8 was 1.625. So pretty early on, all of these divisions started to get close to 1.6 something. And actually, the further and further we got, we're seeing it's getting closer to this term here, 1.618. And the further and further we got, we see it goes 1.618. Okay, the first 3 decimal places will always be that, the further and further we got. Okay, so that's hopefully what we noticed. So this here, this special number that actually we found is the ratio between the terms in a Fibonacci sequence. Okay, is called the golden ratio. Okay, it's called phi. So ancient Greeks were the first sort of mathematicians that discovered this idea, and then Fibonacci found that it was related to a sequence. But they used the Greek letter phi to denote this number 1.618. So it's what we get when we get really, really far along this Fibonacci sequence and divide a number by its previous term, we get this number 1.618, okay? And it's a number that goes on forever, like pi, okay? If you've heard of pi, 3.141, okay? Then it goes on forever like that, but with no pattern in the numbers, no pattern in the decimal places, and it goes on forever. And this number, this special number, okay, occurs in so many different places. Like we've already seen with the spirals, okay, but we're going to look to see where it also occurs in art and in architecture too. So we can see we've got the Mona Lisa here, and you can see that golden spiral, okay? So that golden spiral is increasing at a rate of 1.618. So this width here, okay, is 1.618 times by this width here. So each time the spiral goes around, it's increasing by a rate of 1.618, and we can see that Mona Lisa's proportions are all within that spiral. Okay, so her head height is 1.618. If we take her head height and times it by 1.618, we get the height between her chin and her elbows. Okay, so the proportions of the Mona Lisa are all within this golden ratio. Okay, and we can see it from this other famous painting here as well. So lots of examples. And all you need to do is just take a quick Google search and type in the golden ratio in art, and you'll see loads of paintings that all have, and photographs that all have this this golden ratio in there. Also, like I said, it also occurs in architecture. So we've got the Great Pyramids of Giza, we've got the Parthenon in Greece. okay, and then the Eiffel Tower in France. Okay, if we measured the height from this floor of the Eiffel Tower to the base, okay, and then we times that height by 1.618, we'd get the distance between the top of the Eiffel Tower and that floor. So the Eiffel Tower is in that proportions, and that's because this proportion, this golden ratio, is aesthetically pleasing. It looks beautiful, okay, and that's why so many architects, so many artists use it in their paintings, because it's just a naturally occurring proportion that as humans we've evolved and got used to, and that's why we think that it's aesthetically pleasing and beautiful. Okay, and like I said, it also occurs in us, in the human body. Okay, the human body is full of the golden ratio, and that's what we're going to be exploring today. So if you look at this diagram here, the pink lines represent one unit, and that unit can be anything, okay? So that's one part. The blue part is the golden ratio part, phi part. So each blue part is 1.618 times longer than the pink part that it goes with it. So what that means is if I take, let's say, the top of his head to his hips or to his elbow, whichever you want to say that is, okay, and if I times that by 1.618, that's the same distance from someone's hips or their belly button, really, to the bottom of their feet. So what that means, you can try this yourself. You can measure the distance between the top of your head and your belly button. Okay, times that by 1.618 on your calculator, and then measure the height from your belly button to your head to the floor, and you should see that it's that same distance, that 1.618 times by that first measurement that you did. Okay, and we're going to explore this. We're mostly looking at how our faces are within the golden ratio, and how and looking at how other people, their faces in the golden ratio, and we're going to see who's more golden, who has more of the golden ratio within them. So what you're going to need to do is get a ruler or a tape measure, okay, and some subjects that you can use yourself. So you can use your own face, you can use your parents, your mum, your dad, your brother, your sister, your grandparents. Don't think it's really going to work with your dog or your cat, but you can try. Whoever there is at home, okay, or you could get some pictures off the internet or from magazines of your favourite celebrities, your favourite pop stars, your favourite footballers, your favourite YouTubers, whoever it is, okay. So you just get some pictures of their face, and what you need to do is start measuring these things. So A is the top of your head to your chin, B is the top of your head to your pupil, C is your pupil to your nose tip, so that distance there, okay. D is the pupil to your edge of your lips. E is the width of the nose at your base, so the width of your nose, so that bit. F is the outside distance between your eyes. G is the width of your head at ear level. H is your hairline to your pupil, so I'll move my lockdown haircut out of the way. Your hairline to your pupil. Okay. I is your nose tip to your chin. J is your lips to your chin. K is your length of your lips. And L is your nose tip to your lips. Okay, so you can measure all of those for try to be as accurate as possible, so to the nearest millimeter if you can, for your face, your parents' face, your brother, sister, okay, or pictures of your favourite celebrities, okay, and we're going to find out how golden we are. So if you want to pause the video or go back to the video at this point at any time, you can when you're measuring these. Okay, so these are just the diagrams going through each one. So we've got A is top of your head to your chin, B is your top of your head to your eye, C, eye to your nose, D, your pupil to your lips, okay? So again, if you want to pause the video, go back to this diagram to help, you can. Again, F, you've got your width of your head. So F is the width of your eyes, G is the width of your head, okay, and E is the width of your nose. H is your hairline to your eye, I is your nose to your chin, and J is your lips to your chin, and L is your nose to your lips, and K is the width of your lips. Okay, so you can measure all of those for your chosen people, and then what you need to do is put it into a table like this. Okay, so you're going to compare how golden you are compared to your favorite celebrities, compared to your siblings, compared to your parents. Okay, which of you have more of the golden ratio in your faces? So let's say we're going to compare Messi, our favorite footballer, with our favorite pop star, Taylor Swift. Okay, huge Taylor Swift fan here. So we're going to compare these. Okay, so we're going to measure A and G. so top of our head to our chin, and the width of our head at ear level. So we're going to measure those. Okay, and then we're going to do A divided by G. So we're going to do the height of our head, top of our head to our chin, divided by the width of our head at ear level. So let's say that Messi got 1.62 and Taylor Swift got 1.64. What that means is that Messi is closer to that golden ratio. It's closer to 1.618. Okay, so for that measurement, Messi is more golden than Taylor Swift. So that's just an example. So we do it with all these measurements. So you pause the video, go back to whichever point in the video you want. Okay, do it for all these measurements and find out who is more golden than the other people. How do you compare to these other people? Okay, and then you can work out the average of each one. So we add them all up, add all of these numbers up when we filled in this table, and divide by how many there are. So divide by 7, and we'll get the average. And we might find that Lionel Messi's average is 1.68, while Taylor Swift's average is 1.61. Okay, and what that shows is actually Taylor Swift overall is more golden than Lionel Messi. So that's just an example, but you can do it. You can do it to whoever you like. Okay, you can use real people, you can use celebrities, you can use whoever. Okay, so find out who is more golden than other people. I hope you've enjoyed that video, and I look forward to re-welcoming you to Autumn Park in September. Okay, I can't wait to see all your faces, and make sure, and hopefully when you see me in September, you can tell me how golden you are. Okay, have a good summer, and I'll see you in September.